parsec. Then I have another typical size, which is the size of the single object of the galaxy. And that's the radius is 10 kiloparsec. Okay. And then I have the fact that there is 1,000 galaxies in the cluster. Okay. And then what I put is also the mass of the galaxy, and I said that the mass of it, well, I give you the total mass and you divide, but basically the mass of a single galaxy is approximately 10 to the 10 solar masses, or 10 to the 11 solar masses. And then I also said that the typical dispersion velocity is approximately 1,000 kilometers per second. Okay, how am I going to use all this number? What I want to understand if it's within the cluster, okay, all these single galaxies that are moving around randomly but with a typical velocity of this order of magnitude are interacting with the others or not to a certain extent, right? So that's the problem. Collisionless gas, a perfect gas, and means are they interacting or not? So one way to see it is something very simple that you are also doing for the mean free path of an electron or the alpha. So basically I want to see if a galaxy going through the whole cluster, so say that the galaxy starts here on the edge of the cluster and is going to hit any other of the galaxies before getting to the other side, right? That's one way to see it. Are you following me? Very simple. So one way to see it is, okay, I want to compute the mean free path of the galaxy within the cluster. And the obvious way to do it is I have to put the density of the target. Okay, what's the target in this scatter? The other galaxies. So I put the number density of the galaxies, and then I put the cross section, the heat. So what's the size of the scatter? Now, the trouble arises in when I want to define the cross section of one galaxy with the other, right? So what is the cross section of a scatter between one galaxy and the other? That's the obvious answer, but it's wrong. That's just telling you that a galaxy is not hitting the other galaxy face on. Okay? And that's a good answer for the first layer of the problem, which is what I'm going to compute. I'm going to lead to you the second layer of the problem. So one layer, layer one, is obviously the size of the galaxy, right? So sigma is the surface of the galaxy, so it's P R galaxy square. The second layer is, I asked you perfect gas. What is a perfect gas? I know that even in a non-perfect gas, particles don't exactly hit each other, but they do interact with each other. So there is a typical radius of interaction which generates van der Waals forces. Okay? So the second layer of the problem, which I'm not going to compute, but I'm going to compute the first layer, is what the radius or the area of action of the gravitational forces, which is the only interaction that I have. And in that case, I compute the mean free path for this new area of interaction. So this is, let's call it sigma for the area of interaction. So when can you say that two things interact? Sizably. When the effect of one over the other is of the order of magnitude of their state, right? If our interaction is financial and my worthiness is $100,000 and you give me $1, we have not interacted. It doesn't change my capital. Same thing, if an electron, non-relativistic electrons, hits a proton, it's not going to move it. For the electron is the end of the world, but for the proton that doesn't change anything because its mass is 1000 times. So I would say that to the extent of this interaction, I must define the distance where the gravitational interaction between the two is of the order of magnitude of their current state. And their current state is defined by their kinetic energy, right? So I can define the radius of interaction between the two galaxies as the radius such that the potential energy of the other galaxy is equal to the kinetic energy of the galaxy. Well, they're all the same, so this is easy to find, right? So here you put the mass of the galaxy, its velocity, its typical velocity square, and here you put the m of the galaxy, which is the same, divided r, and this is the r you want to find. And at that point you put this r into this new expression. Okay? This is the second layer. It's a more refined layer. The first layer is more obvious, when the two galaxies just hit face on. Okay? I'm gonna give you the answer for this part. I'm gonna perform the exercise. Actually, I'm not gonna perform the exercise because now, otherwise I'm cutting time short. But that's the solution. Actually, this thing is easy to solve, right? Here you put the number of galaxies per parsec, which is the number of galaxies that we have computed, divided the total volume of the cluster, which you can find, multiplied by pi r galaxy square. Okay? And the volume of the cluster, please don't tell me I have to spell it out because it's perfectly spherical. Okay? And as a matter of fact, I did these numbers this morning, and I find out that if you put these numbers in here, you get that this is approximately 10 megaparsec, if I'm not mistaken. Okay? That basically means that for this part of the problem, the answer doesn't really change. One galaxy can cross 10 times the length of the cluster before hitting another one. Or seen another way, it just means that the probability of a galaxy hitting another one is 1 out of 10. That basically means it's a sizable chance, but it's not dramatic. That basically means that 90% of the galaxies are not going to be hitting the others. That basically means that it's not a perfect gas, but it's reasonably collisionless. Okay? Also consider the fact that I've taken the face-on radius and galaxy might be passing side to side, right? So this is being conservative. And as you can see, this is very simple numbers that you can do with very simple physics. Okay? So you can convince yourself that this is correct, that clusters are collisionless pretty easily. Okay? So now it's time to start really with the new material for today. And so yesterday I tried yes. So yesterday I introduced you to one part of the problem. Okay? And one part of the problem is we see local objects, clusters, galaxies. This is not embedded in a cosmological framework. I just observe them in a close-by universe. I'm not trying to attempt any cosmological interpretation. And I derived the conclusions that in both systems, all sorts of galaxies, big and small. I showed you the case of the spiral galaxies, but you can do Jeans analysis on smaller galaxies and individual clusters. You derive the fact that there is something missing. Okay? Today, I'm going to put it in a cosmological context and show you also why this evidence stands in a cosmological context that requires a theoretical framework of many other observations. And on the top of it, it will give me a strong handle to show you that it cannot be anything we know in the standard model of particle physics. Okay? Yesterday I showed you, and I'm going to get back to this at the end, that it can't be planetoids. It can, in the galaxies and in the clusters, whatever is this missing mass cannot be planetoids, cannot be compact objects. Okay? I'm going to get back because I think many of you were confused. But today I'm really going to show you the proof that it cannot be anything of the standard model. One moment to break the ice and wait for the last person to gather. Yesterday, I was telling you you're young and probably you don't know what a vinyl is, so I want to perform an experiment. I'm going to show you two objects, and I want immediately, as soon as you see them, how many of you see a clear relationship between these two objects, okay? Don't think about it. Just go. It's less than 1/3. It doesn't work, Martin. We're old. We're old. This is the relationship. You rewind them with a pencil, okay? All right. So, and then there is another point. At some point in this class, if I have enough time, I'll show you a connection, a deep connection between this class and the neutrino classes. But before that, this is a question, this is more to the organizers. I want to show you another connection that arose in 2006, and I want you to spot the outlier in this picture. So there is some disturbing material in the next picture, I warn you. It represents two very well-known neutrino physicists. One that is not very well known, but is in between the connection between neutrino, and one outlier. Spot the outlier. So this picture was taken in Neutrino 2016, and as you can tell, it's been taken in the United States. Sergio Pastor is coming from Europe, is completely jet-lagged. I was being there, and I was much younger. Olga is super excited, and the reason is that we had just met Javier Bardem, who was shooting a movie, No Country for Old Men, and invited us on the set of the movie, where we didn't go, because it was the last day of Neutrino 2016, which is the conference where I learned about the experiment you were talking about yesterday. The one to discover neutrino, to observe neutrinos during the explosion of atom bomb. It was extremely interesting conference also because they put together old and young people. It was 50 years from the discovery of the neutrino, and we got the chance to talk to people who had been taken part of the Manhattan projects. We're very young physicists then, and so we talk about the physics and the politics of the time. So let me get back to today's class, but also let me give a very delicate announcement. And before giving this announcement, I want to make sure that you understand that nothing of the kind has happened, and we are sure nothing of the kind will happen, but we want this to be a very safe environment. So you're going to be together for 2 weeks. If in your community something happens, of someone else's behavior offends you or doesn't fit you for any reason, feel free to report to me. And if you don't feel comfortable with me, you can talk to Carla. We are here to listen to you. So if anything happens, we are here, we take it calmly, we can take it privately somewhere. Okay, nothing has happened, we believe it will not happen, but you always wear a safety belt in case that something happens. Okay, so yesterday I showed you that galaxies require the existence of a non-visible component, and the clusters do the same thing. I want to make sure that it's clear that for galaxies I used kinematic measurements mostly, and spectroscopic measurements for the luminous component. For clusters, at the beginning I showed you that you can infer the same thing using kinematic measurements and spectroscopic, but eventually I obtained the same information with weak lensing and X-rays. Okay, so I'm not using kinematics with the clusters anymore because the new observables are much more refined. And I took the clusters individually. Okay. And also separately, I showed you that if you use microlensing in galaxies, you can see that whatever the missing matter is, it cannot be planetoids or other things. Now I want to go a step further, and I want to show you that when I take clusters, I can have another proof, another constraint on what dark matter is not. Okay? And the thing is that typically when actually, you've just performed the experiment and seeing that clusters are collisionless with respect to galaxies, okay? So, what happens if I throw one cluster of galaxies against another cluster of galaxies? The systems have the same density, right? So, are galaxies going to collide or not? Not going to collide, right? So, they just go through each other because the chance that one galaxy hits another galaxy is very small. So if this bulge cluster has a typical, but all galaxies are going in one direction, so the item is going in one direction and the cluster is going in the other direction, cluster 2 is going in the other direction, they're not going to meet. But most of the mass in the cluster, visible mass in the cluster, is made by the gas. And the gas is sizable to interaction. Thomson scattering, basically. So what happens is that the gas in the cluster gets trapped in between because the hot hydrogen in the intracluster gets stuck with the intracluster. So what you're seeing here, this is the famous bullet cluster. I don't know how many of you have heard it, but what's going on in the bullet cluster is that you have two clusters that have typical velocities. One, I know that the galaxies belonging to these clusters are all going in one direction. The galaxies belonging to this cluster are typically going in one direction. So you know that they hit at some point in the past, and you know they've gone through each other. So one thing, I take all the galaxies in here. They don't make most of the mass of the cluster that I see through lensing. And I can see that most of the mass of this cluster is here, together with these galaxies. Okay? And the other case is true. So I have another cluster. I make weak and strong lensing with this cluster, and I can see, so these green lines represent the isodensity surfaces of the matter as observed from lensing. Okay? So whatever makes most of the bulk of the matter. And they're separated together with the galaxies. Then I look at the X-rays, and as I was expecting, the gas is stuck in between because the gas self-interacts. There is a friction, okay? So whenever I'm throwing one cluster against the other, the galaxies go through, the gas gets stuck in the middle, okay? This is visualizable with this, which is a very, very nice visualization that Tom Abel made, not Tom Abel, actually, John Wise, who was his student. Okay, so you're seeing spheres. They overlapped a sphere of blue, which is the dark matter and the galaxies, and the red, which is the hot gas, to which is assigned a cross section, and it's just throwing these two spheres one against the other in the simulation. It's actually a simulation, so it's simulating the physics. It's just saying the blue stuff doesn't interact with itself and with the gas, only gravitationally. The red stuff does interact, okay? So the red is the equivalent of the gas, the blue is the equivalent, if you want, of the galaxies and the dark matter. The reason why I'm saying that dark matter cannot be interacting with itself is the following. Look at this. Is that, as you can see, most of the bulk of the matter stays with the galaxies, right? In this hit, most of the bulk of the matter stays where the galaxies are, not where the gas is. That is basically telling you that whatever is making the bulk of this matter, it's not self-interacting, at least at the level needed for getting it stuck. Okay? So it's telling you that whatever is this dark matter is not self-interacting like the gas. It's collisionless to that extent. Okay? You can obviously quantify this statement, but that's the basic reason. You don't only have one system, you have a host of systems. So you can derive a quantitative number, so you can basically put a constraint on, if you make up the number, you cannot constrain the cross-section. You can constrain the cross-section divided the mass, and obvious reason is that you have a number density of particles, so sigma v over the mass. And you can put a number, okay? So there is a number that you can quote here from these studies. Not only the bullet cluster, is many of them. It's a big bulk of systems, okay? And basically, that is telling you that whatever is the dark matter is collisionless. It's not interacting neither with the gas, neither with itself, okay? And this is important to understand. This is a limit, this is a constraint on the self-interactions that is of the order of the Thomson scattering cross-section if I put here a particle of 100 GeV. So if I change the mass, the cross-section will change because this number is what I get from the experiment that I'm constraining this. But it's typically a number which is not crazily low. It's enough to tell you it cannot be anything belonging to the standard model because otherwise it would interact. But it's not prohibiting you these particles to be weakly coupled to the matter. So when people say dark matter is collisionless, it's meant astrophysically. Okay? Right? You can take this number that I'm not giving you here, But if I put a mass of approximately 100 GeV here, I get the Thomson scattering cross-section here. It's just telling you that it has to be below Thomson scattering. Okay. On the other hand, from this system, which is again, it's a local system, is not in a cosmological context as though I don't need to interpret it cosmologically. I get already information on what the dark matter is not. So at this stage, I already know, one, that it cannot be compact objects. This statement needs to be a little bit more quantified. So some ranges of masses are prohibited, but for the moment, let's say. And also, the self-interaction interaction with the gas must be limited. So it's collisionless astrophysically. All right. Okay. Yes. Compacting means that the radius of the object must be below the Einstein radius for microlensing, which basically means rocky, a sun, a mini black hole. That's compact. That's a good question. I talked about microlensing constraints yesterday toward the Large Magellanic Cloud. I'm 31, but I'm gonna get back today if I have time. Okay. But this is a more powerful thing because actually by itself, actually these constraints doesn't rule out the compact objects because they would be also collisionless to that extent as galaxy would be, but it's telling you cannot even be a diffuse component with a certain interaction. So it starts ruling out a series of mundane explanations like hot gas, like cold gas. One of the possibilities is, okay, in clusters is a cold gas that is gotten there somehow, but if it was cold gas during this interaction, it would heat up and you would see it, and it's not, because it has to be segregated. It has to go together with the collisionless parts, the galaxies. Okay, so this is all local, and this is all invoking physics that is relatively easy to understand. Now, I'm not asking you a leap of faith because faith doesn't belong to this room, but you will have to trust that what I'm telling you about CMB and the next part, which is cosmological, is true. And if there are some deep elements that you miss, I will try and answer your questions, but it's going to be extremely difficult to give you a primer on CMB in 1 hour. So this is some thought-provoking thing if you're really interested to go to a cosmology course and grasp this physics, okay? So, okay, these are the actual constraints from the clusters. You can put the constraints on the self-interaction cross-section. That's a Nature review. And let's not go to that slide. Well, let's go to the cosmological context before getting the CMB. You are familiar with this slide, right? Okay. How many of you know that this slide is not true for not most of the life of the universe, but at least 2/3 of the life of the universe? Okay. That's because this is the energy components, the energy density components at redshift 0. Okay, things that have a relativistic equation of state or a non-relativistic equation of state expand differently. Their energy density expands differently with the expansion of the universe. Okay, so this plot is different. So photons are going to account for more than the energy density of the universe back in the past and matter less, and so on and so forth. This is something you should know from cosmology to get a grasp of some of the things that are going on. And if you want, it's because if I take a box, it's a clear example is if I take a box full of photons and I take a box full of particles and I expand this box cosmologically exactly the same way, the number density of particles and the energy density of particles, which is the mass of the particles, is gonna just go like 1 over r cube. The number of photons is gonna go like 1 over r cube, but in the meantime, the photons are stretched. And since the energy is h ni, which is h1 over lambda, and since lambda is changing, the energy density of the photon is decreasing. The energy of the photons is not conserved cosmologically. So this is a quick primer to think that the energy density of different components with different equations of state evolves differently. Okay, and I need this because today the expansion of the universe is driven by lambda. Back at the CMB, you are in a moment in which basically matter, all the matter, everything that exerts gravity and it has a non-relativistic equation of state, and relativistic stuff are pushing the universe. At the CMB is a little bit more matter, but the radiation matter equality comes at that time. Okay, this is important to know. What is this? Who understands what the CMB is? This is a map of the CMB. Very little people. Okay, so you heard that the CMB is a picture of the universe when the universe is very young. That picture is nothing else. So back then, let's go as back as we can. So the universe, if I'm seeing it rewinding, the universe is becoming hotter, hotter, hotter. I go very close to the Planck time, very high temperature, say, I don't know, very, very, very high, much above ionization or whatever you can think of. And it comes to a point while the universe is expanding that you go below the threshold for ionization. Okay? All right? So this is time. This is the temperature of the universe. This is something like GeV. This is MeV. This is KV. This is 10 electron volts. This is 1 electron volt. So the temperature of the universe goes something like this. Okay? So what happens here? When the universe is at the temperature of GeV, what's going on? Certainly like quark confinement. Around here, weak reactions stop working because they freeze out. That's a typical energy scale. And around here, nuclear reactions stop working, but still the material is all ionized because the photons around are very excited. And around here, electrons and protons recombine. Okay? So that basically means that the mean free path for a photon that usually scatters off the electrons, becomes infinite because the atom is recombined, the electrons scatter mostly over, the photon scatters mostly over electrons, the electrons are not around anymore. So all the photons that are produced at the ionization, so the ionizing photons stream away in the universe. And then the universe expands and they cool down and we see them today in the microwaves. Okay? There is one important thing. Since they are all produced in a very short time and the universe is basically a black body, if I'm looking in different directions of the sky, I would be expecting to be seeing exactly a black body of exactly the temperature. Okay? And it doesn't seem the case from that picture. First of all, because that picture is misleading to a certain extent. And second, because the universe is not perfectly homogeneous and isotropic. Okay? So, first of all, if you were looking at that picture with 1-digit contrast, you would be seeing a perfect sphere. Okay? It would just be uniform. Beside the center there, which is our galaxy, because this picture is realistic, whereas this one has erased the center of the galaxy where there's a lot of contamination. If I were giving you contrast as the first digit, at the second digit, you would be seeing a perfect flat thing. Okay? It's a perfect black body. You go to the fourth digit and you see a small contrast. But now I'm telling you that the CMB is produced in a very short time and it should be the photons of ionization, which is one frequency. So it should just be a black body around that frequency. The reason why I'm saying this, and this is extremely important to understand the matter part, is that the universe is not perfectly homogeneous and isotropic. So there are seeded a certain amount of delta, which means density, actual density over average density, okay? An over density of the order of 10 to the minus 4, okay? And they are also a function of the spatial scale. K is the inverse lambda, okay? So if you want this, there's big and small perturbations of density. Now, so I have a big perturbation of density, I have a small perturbation of density, I have average density. What matters is that when the process that dictates the photon of the CMB to be produced is the ionization. So locally, the photon doesn't know where he is. It just feels whether it's hot or cold, and then it recombines or not, because that's dictating the electromagnetic interaction. So wherever the photon, wherever the electron, well, the photons have all the same energy, but basically, wherever they are at some point, they can't scatter anymore and they stream to you. Now, if originally they were deep inside a big potential well, when they come out of it and when I see them here, I will see them a little colder than those here, okay? Just because they have to climb outside of the gravitational potential. And the fact that they don't have mass, it doesn't affect the statement, okay? So this is called Sachs-Wolf effect, and I invite you to look it up. But for what is most concern of this class, what matters here is that when I look at the density, at the photon density contrast of the CMB, I am basically looking at the density contrast of the universe. Okay, potential wells. The potential wells are dictated by everything that exerts gravity. Okay, can you see the connection with what I was saying now? With the subject of the class. Okay, everything. I don't care what it is. Right? The important thing is that it exerts matter. So if I get information about the distribution of the potential wells, I get information about everything that exerts matter. Doesn't matter what it is. The important thing is that it's coupled to gravity. Okay? So if you want, it's the equivalent of measuring the total rotation curve of the Milky Way, or the equivalent of getting the weak lensing. It's the total matter, it's the total mass. Okay? And one important thing is that obviously what I look in the CMB is typically the power spectrum, so I can do the Fourier transform of those sorry, the words escapes me, of those anisotropies, okay? And this spectrum really depends on the correlation and the depth of these potential wells, okay? And in fact, it's extremely sensitive to something which is called the matter density, okay? Now, I understand that if you don't really know what is CMB, I can't really explain you how to form the peaks in the CMB, but what happens is that this spectrum is what I do observe, and there are not easy to understand reasons. And so if I change omega matter, that's what happens. Okay? Okay? So here I'm changing the fraction of the energy density in the universe that is made of matter. Okay? The cosmological parameter omega matter, everything. And as you can see, is really changing the shape. And when I go to the data are extremely precise. So although it looks like a little bit like hocus pocus, it is not, because the important thing to understand is that basically the gas inside, well, let's leave it at that for the moment. What it matters is that if I increase the amount of matter, I increase the potential depth of the potential wells. So that map of anisotropies will look different. Okay? And what you're seeing here is just the Fourier transform of it. Okay? Is that a physical enough explanation to accept for the moment? Okay? And if it leaves you unsatisfied, take a CMB course or ask me later, but that's I can't really compact everything into that. Yes. Yes, that's a very good question. So, well, omega matter, I can take the cosmological value, so I can co-move his eyes, but I am measuring whatever is at the CMB. That's good. That's also a good point. So obviously at this point, I'm measuring the properties of the universe at redshift 1000, okay, which is the redshift at which the universe is around the ionization. Okay, so conclusions that I'm going to give about this happened back there and not today. Whereas everything I've done yesterday was happening at redshifts around 0, like ourselves, close by galaxies and clusters. Okay? So with this, I can measure the total content of matter. Now, the point is that it's not telling me anything as long as I don't know what the luminous matter is, right? Because otherwise I don't have a problem. I mean, I have only one observable. And now my mind is set on understanding whether the total gravitational matter is different than the visible one. And in this moment, I mean standard model, gas, anything. That at that point is just gas around. There are no stars, there's no planet, nothing, okay? It's just gas. So, as a matter of fact, the depth of the relationship between these two peaks can tell me how many baryons there are. Baryons meaning anything that has an interaction with the photons. And the reason is, but I'm not going to use this because this is a little more forward, and also because when I was a student, this was not possible with the data, so I had to use something else. But the reason is, and then I'm going to use this also later on, what happens is that, imagine that there is this potential well, okay? Now, everything that is in this potential well tends to go down, okay? So I have two particles. One particle, I'm not calling it dark matter, one particle is sensible to the interaction with the photons, and one particle is not, is collisionless, is whatever is in the cluster. I just know it's collisionless, it doesn't interact with the photons because I'm not seeing it, and it doesn't interact with itself, okay? So this is what I will later call dark matter, but for the moment. So what's going on? The particle that doesn't have any other interaction but gravitational, it will just go down to the dip of the well. At most, it will climb up, but it will basically stay here, okay? And if by some reason later on more matter is accreting into here, and the potential well goes deeper, this stuff will keep falling into it. What happens instead to something that is subject to an interaction of the photons is that they are going down. But if you are right above, right before the CMB is formed, so there is a lot of photons around, and this thing can interact with the photons, it will feel a pull down, but it will feel the pressure of the photons, okay? So it will actually be pushed outside, okay? And this is what, to a certain extent, is called baryon acoustic oscillations. That's not the whole story, but that's the underlying physics, okay? So as you can see, the behavior of the total matter and the behavior of something that is matter and also has interaction with the photon or itself is different, okay? And that's what gives different features in the CMB. But for the moment, I don't want to use this property. I'm just using the fact that by fixing the data, I can fix the whole content of matter. I'm not going to go to something more refined. And since I have the data very well, I can fix the total amount of matter. So CMB gives me the total amount of matter, okay? This is a sketch that I took from Ravi Shet's class of where the different parts of the CMB give different informations. But for the moment, I just want you to fix in your mind that the CMB at 0 order gives me omega matter. And this omega matter is, in cosmological terms, everything and only stuff that interacts gravitationally, okay? And now I'm here, around the ionization part. There is an interesting thing. What happens earlier in the universe is that, as I said, the farther back you go, the more you have energy, so the more heavier or stronger interactions are active, okay? So well, actually weaker interactions. If I am around the MEV, when the universe is hotter, what's going on at this stage? Electroweak. Good. So around this stage, you have that somewhere around before, there's only neutrons and protons. You can compute the statistical equilibrium abundances for all the elements, but basically that gives you that there are only neutrons and protons, okay? And exactly as when I was here, there was this reaction, electron plus proton going into hydrogen atom and vice versa, which is there is enough energy around to make it go both way, and then below 10 electron volts that freezes and it just goes this way. Okay, here I have another reaction or other reactions, which is this one. I need an electron, I need it here, and all of its flavors. Okay, right? And it's very active. The moment I fall below the freezing, the temperature for this reaction to go freely, I'm only neutron decaying. Okay, I'm not in equilibrium. Okay, so, and therefore I'm only left with neutrons and protons if the temperature is below 1 MeV. Okay, keep following me. This is the part that is connected to the neutrinos. So yesterday we were talking about this. First of all, this is interesting per se because exactly like the photons of the CMB are streaming away when the electrons are not around, the neutrinos are streaming away when the weak reactions are frozen because they don't hit any more targets, right? So this is the cosmic neutrino background that Andre was talking about. But the other interesting thing is that right after the MEV, there are neutrons and protons around. And the weak reactions are sort of frozen, but still there is enough energy for nuclear reactions to take place, okay? So what's going on is that until a certain point, when the temperature is something like 0.1 kilo electron volt, the neutrons and protons around, while the neutron is decaying, are just doing nuclear reactions, okay? And when the temperature is low enough, they stop. So the whole universe between 1 mega electron volt and 0.1 kilo electron volt becomes a huge nuclear reactor for fusion, okay? Where the temperature is constantly going down and the chemical composition is constantly changing because you have a neutron and a proton, you're throwing it against each other, you make a deuteron, so you have neutron, proton, it goes into deuterium, then you have small abundances of deuterium, you add protons or you add neutrons, and you go to hydrogen 3 and you go to helium 3. Okay, so this is known as BBN, Big Bang Nucleosynthesis, and I don't like this name because I don't like the Big Bang. I like the idea is primordial nucleosynthesis, is early phase of the universe. Okay, so why is this interesting for our problem? First of all, don't forget that I told you that during the CMB, whatever is driving the expansion of the universe, so the leading term in the Einstein equations, is more or less radiation and matter at the same time. But during this phase, at an early phase, matter is not dominating the energy content. Everything that is dictating the expansion of the universe is radiation, radiation-dominated era. Okay? Relativistic species. Relativistic species at this epoch are photons and neutrinos. Okay? So one thing, whatever are the details of the production of this neutrino background that I was talking about, it will depend somehow to the amount of relativistic degrees of freedom in the bath. And since I know how many photons there are, and since I'm not sure of how many neutrinos there are, I've observed 3 species, but there could be more. That's extremely interesting because the details of that we were talking about yesterday can give me details about neutrinos. But the second point that is extremely exciting is that let us say that I know how many relativistic degrees of freedom there are. So I know omega radiation here. That means that I know the expansion speed of the universe. I can predict the abundance of light elements because they are dictated only by the time this thing finishes. Okay? Because I'm building nuclear reactions. Whatever is left over when this reaction ends is going to be what I observe around if I'm able to observe them, okay? But the point is not entirely true that the thermal evolution is the only thing. There is one more thing that I need to know because I'm throwing 1 neutron against 1 proton, I'm throwing 1 proton against 1 deuterium. There is one more element, and it's just the number density of this stuff, right? It's a mean free path, I want a reaction. So The details of the freeze out, the details of the light elements that are left over by this nuclear phase depend on the total amount of radiation, which I know is known physics, okay? Relativistic degrees of freedom, often known as ineffective. But it will also depend on the abundance of neutrons and the abundance of protons. And they are just related to the total amount of gas. The gas, the real gas, whatever interacts, not whatever is matter. I'm not seeing a gravitational interaction here. I'm seeing nuclear interaction, I'm seeing electroweak interaction, I'm seeing everything that is the guts of the universe, not gravity. That's for the angels. Okay? So the details of the primordial nucleosynthesis, the light element abundance, will depend from what I will call omega baryon. Okay? With baryons, well, like baryons, the heavy ones, they could be the mesons also, like anything belonging to the standard model of physics, but mesons would decay very quickly. So only the baryons are left over. Okay? So primordial nucleosynthesis, which is tracing how the elements evolve. Actually, no, this is not a good plot. So here you're seeing how the elements evolve with time. So you can see here that I am fixing this thing that I don't know. I'm saying I don't know how many, what's the relative abundance of baryons of matter. I fix one value and I see what happens, and then I change it every time and I try to derive the real value from observations. What's going on here is that I can see that I am building deuterium out of protons and neutrons. So protons and neutrons at very high temperatures are there. The neutrons start decaying. It basically fuels the production of deuterium. Okay? And the deuterium, after the deuterium, I produce helium-3 and I produce tritium, so which is hydrogen-3, and I produce beryllium-7. And by some time, when the universe is cold enough, the reactions are frozen. And that's the light element abundances. These final numbers change if I change this parameter here, because if it's denser, I will have more reactions. So then the abundances that I expect here change according to omega b, okay, to omega baryon. So when I go and measure these things in space, which is something that I do, this is how the final abundance would evolve with eta, which is actually the number of baryons per number of photons, and you can, it's a proxy for omega baryon, okay? Read omega baryon. So as this parameter change, the final abundance changes. So primordial nucleosynthesis is a powerful tool to tell me what the normal matter is. Okay? Good? Are we on that? Because it depends on nuclear physics. So it must be the real matter, whatever, it's not gravity. And the thing is that if I take the omega b that I get from BBN and I compare it, I am naive. I don't know there is dark matter. I'm just a cosmologist. My astrophysicist friends don't tell me anything. I measure the BBN and I get the number of baryons. I measure the CMB and I get the amount of total matter and say, well, look, the universe is working. It should be the same thing. And no, it's not the same thing. Okay? So again, I'm left over with a problem. Again, I can measure this number already from now. Today with the data, I can measure it from the CMB because I see the Baryon Acoustic oscillations. But the classical test has been primordial nucleosynthesis. Now, you should give me an observation. What's your name? Manuel. Because you told me, well, but I was observing CMB, so I was telling you the matter abundance at the CMB at redshift 1000, and now I'm telling you the amount of matter that is around much earlier. So theoretically, I'm not testing the same time. Well, as a matter of fact, I'm not testing the same time of the universe. Good, that's a good point. You can imagine alternative cosmologies, but phase values, we assume that the things don't change. And in fact, if I use the CMB self-consistently, I get the same number. But it's important to know that from cosmology, again, I get the same problem. And the thing is that unlike clusters of galaxies, unlike galaxies in which I can say this matter is luminous. I'm measuring a luminous matter, and okay, there must be something that is not luminous, you don't see it. In this case, I'm not observing luminosity, I'm just using the intrinsic properties of the standard model. Whatever is standard model must be doing light elements, or coupled to the photons if you're using the CMB. So it's entirely, completely different physics. I'm getting rid of any sort of observational things that might be related to the gas around the galaxies or the planetoids. And actually, if I take the number, it basically is the same order of magnitude that I have in galaxies of clusters. Someone yesterday asked me if in different galaxies I have the same ratio, and I said at face value it is. And at face value, the difference between these two is the same ratio that I get in clusters of galaxies and galaxies. Okay? So this is again telling me something extremely powerful about the nature of, well, about the fact that dark matter exists, again, because I have the same problem in cosmology, but also about the nature. Because I started off saying, okay, it cannot be planetoids, it cannot be small black holes because I'm using microlensing. Okay. Then I go to the clusters, I'm saying it can also not be cold gas that I'm saying, and it has to be collisionless and not self-interacting. And now I'm going to the CMB, and now, yes, I'm using a cosmological context. I'm using one more framework, okay? And I'm telling you, but come on, this thing is very, very strange. It really, I'm using the properties, the intimate properties of the standard model of particle physics, and it can't be that. So, in a way, I like cosmology, and well, once you get to understand the details of the CMB, I like the CMB by itself because the different peaks can tell you this information self-consistently, because it's the ultimate proof that dark matter is there and it cannot be baryonic. Okay, it cannot be anything belonging to the standard model of particle physics, with only one exception that I will talk about at the end of this class if I can. Okay, all right. I hope I'm sort of convincing you. But again, so 3, cosmology. So baryonic. Okay. Are there any questions up to this moment? I don't know if there are no questions because I wasn't clear or because everything is clear. There was at least one question that could help me. Good. Let me take the microphone.
The neutrinos are baryonic matter or not? I don't really.
That's something we're going to talk about later on. I'm going to show you why they don't contribute to the baryonic content, in fact. So they do not count for the primordial nucleosynthesis. So in principle, at this stage, they could be the dark matter. But everything I've said up to this moment, they can be. Because they're non-baryonic, they're not participating of the they're not participating of the restoring forces in the CMB, so they don't generate this additional peak that I didn't talk about. And they do not participate, well, they should not participate of the primordial nucleosynthesis, right? So that's a very good question. At this moment of the game, neutrinos are perfectly fine to be the dark matter, okay? Any more questions?
Hello. When you said that dark matter doesn't interact with itself, what exactly do you mean in the collisionless gas of two different clusters?
If if whatever makes it, imagine that it's another, we call it a particle X, and if this particle X had an interaction with itself, so hydrogen and electrons have Thomson scattering, right? So if it interacted through a dark photon or something with itself, at that level, it should get stuck. It should heat itself up, right?
But between the four interactional forces, it does interact
It does not
gravitationally.
interact with the gas, otherwise it would get stuck with the gas, and it doesn't interact with itself, otherwise you would have this blob. Maybe you don't see it shining, but you would see the weak lensing would tell you that it's there, and instead it's not there, it's there, right?
When you say that dark matter is not baryonic, you are saying that it not interact in all the four ways of the standard model? No.
So I'm trying to point out to the BBN, that's a very good question. Why am I saying baryonic? Because count the particle of the standard model, right? You know all the particles of the standard model. At a temperature 1 mega electron volt, the only stable particles around, everything that the standard model is neutrons and protons, right? So the BBN is a barometer, is a scale for everything that belongs to the standard model. So whatever eludes primordial nucleosynthesis is eluding the standard model of particle physics. Because I don't expect anything of the standard model to be there, right? So whatever I'm measuring through the primordial nucleosynthesis is whatever I'm expecting from the standard model, okay?
Just because the presence of dark matter could not change this radius interacting with standard model.
If it has a sizable interaction, yes, but we rule that out. As a matter of fact, what you're saying is very clever, because there are specific models of dark matter in which you can elude the cluster constraints but coupled to the standard model. But again, they are not the standard model. It's a specific type of dark matter, and I'm not getting into that. I'm just giving you the picture that I get from the standard model. From the standard model, I expect neutrons and protons to interact, and I expect that their density is depends on that their final abundance is in a cosmological depends on how many there are. I change this number, period. And during BBN, dark matter doesn't do anything. It's not pushing the universe, which is radiation dominated. It's not interacting with the baryons, with neutrons and protons. Not doing anything. I'm just using the information how many baryons there are around and compare it to how much gravity there is around at a later stage, admittedly. But I'm not having the dark matter interacting anything. I'm not including it in the game. I'm just measuring the gravitational potential at redshift 1000 somehow, measuring the amount of matter from the standard model at redshift 10 to the 6, whatever it is, somehow else, comparing the two and saying the matter is not the standard model particle, period. I'm not saying what dark matter is. Actually, today I'm telling you what dark matter is not. Tomorrow, Farinaldo is going to suggest some form or shape. If it's vegetal or animal, and then on Thursday is going to call it a hippo or a banana tree, but right? Respecting what I'm saying today. So he's going to build models that respect this. And there is one more thing that dark matter cannot be that I want to tell you before I go today. Yes.
How does the baryonic acoustic oscillations contribute to this evidence?
Well, it affects the spectrum of the CMB. So basically it's the ratio between the third and second peak, because it's restoring a little bit the power, and but we can go to that. Okay, that's what I'm saying. I don't want to get into the details of the CMB, because if I have to explain what CMB is, already the first peak is difficult to build up. But it is with that. we can talk about it later on. But this is something that flash. Like if you're interested in the problem, CMB is actually very extremely important for cosmology, and also a dark matter probe. So when you're going to your cosmology course, if you're excited enough, take your cosmology course and pay a little bit of attention to it. Okay, let's just put an eye on it. Okay. So yesterday I promised to give you a list of flash of how this scenario is consistent, because right now I've been talking about cosmology, I've been talking about what dark matter is not. Actually, this is a consistency test of how omega baryons from primordial nucleosynthesis and Planck, they are perfectly consistent. This is the paper that came out a few days ago, the Planck legacy paper. But disregard that, which is a little detailed. What I want to talk about is another thing right now. So far, I just told you that something is missing in galaxies, something is missing in clusters of galaxies, something is missing at the cosmological scale, okay? And it cannot be planetoids, it cannot be gas, it cannot be standard model particle physics. So what would any sane person say? Any normal person would say, if you have a mismatch from anything gravitational and everything matter, gravity doesn't work. At this point of the game, the only logic conclusion, zero order, is it's modifying gravity. Right? The most logical thing, not the particle. Right? The point is, it's extremely difficult to modify gravity in a way that works on the CMB, at the cluster scale, and at the galaxy scale. Okay? I'm gonna try and give you an overview of the two sides. The point is the coherence of the whole scenario. When people throw you, but I can fix the galaxy by modifying gravity. You can, but then you cannot fix the clusters. And if you manage somehow to fix the clusters and the galaxies, you cannot fix the CMB. There's no way. Okay? So the dark matter scenario is extremely powerful, because without knowing what the dark matter is, I still don't know it. I know what is not. I will just postulate that it's a particle that is not the mass of a planetoid. It's in a form of a particle, so it can be 1 electron volt, it can be 10 giga-electron volts. It just doesn't interact with anything I'm seeing but gravitationally. I throw it there, diffuse together with the gas, such a way that has a perturbation of the density, an over-density spectrum that respects the CMB. I take it from observation, I throw it in, I let these things evolve. So I let this gas, which is only interacting gravitationally on the top of the normal gas, okay? And I can see that it grows structures and it ends up in gravitational potentials of the size of the galaxies, of the size of the cluster galaxies, that resemble the properties of what I'm saying. And there is nothing, there is no way with any modification of gravity known to the scientific community up to today that can do the same thing. That's not a proof, but it's a consistency check of the scenario. And I want you to take this home. Okay? So, at this point, I am around the CMB. So this is the panel with what we've learned so far, which doesn't seem to be much. Okay? And let us say that I am at what I see. I want to go as far back in the past as I can see, and that's the CMB. What am I seeing? I'm seeing, as I said, a map with the photon energy anisotropy distribution, which corresponds to a density anisotropy distribution. That basically means that I have a distribution of gravitational potentials, which I can call, this is the potential, and obviously I can see it in terms of densities, correspond like this. like this, okay? This is the density rho, and I can write it down in terms of over density, so the actual density with respect to the average density, okay? This is what I'm seeing. My one minus that, thank you very much, right. 1 minus. All right? But the important thing that I have this distribution of potential wells. I can write down a power spectrum of this thing if I just the Fourier transform of that space. But the thing is that what's going on? So here, this stuff, so the whole universe is filled in equal measure of what I'm calling now the dark matter and the gas. They're just overlapped. So I'm assuming that there is everywhere there is this more or less the same content, but the same ratio is equal in all this perturbation. And when there is a density perturbation, it's equivalent. So the amount of the fraction of this thing is the same. What happens to this thing as time passes? Sure, but there is one additional effect. At this in this moment, these things are big enough. They're very big. The spatial scale is big. It can change, but it's sizable. So they feel, on one hand, the Hubble expansion, and on the other hand, the pull of gravity. Okay? This is important to understand. So if there was no Hubble expansion, it would be relatively easy to predict how each one of these falls, and it will depend on their size or over density, and they will collapse and become nonlinear. Okay? As a matter of fact, there is the Hubble expansion that affects differently different scales. But as you're saying, as time grows, I expect this density contrast to grow. Okay? With two minor effects. Since there is the Hubble and the competition of Hubble and gravity that have different effects on different scales, it's not trivial which one of these is going to grow first, if the small perturbations or the bigger perturbations. Okay? It turns out that if you sit yourself in a cosmology like the one that you believe just from the CMB again, the smaller perturbation will collapse first. Okay? But there is one additional fact. So whatever will collapse under the effect of gravity and become a self-consistent item, it's the smallest first, and then later on the bigger one. But there is one other thing that I'm not considering so far, is that this stuff that is around has a velocity. It's non-zero. Okay? It might be very cold, but it's non-zero. So what happens if the velocity of this stuff is bigger than the potential depths of the overdensity? It escapes. So okay? So, or if you want, you can say it in terms of potential. No, that's the potential. Anyways, you can say in terms of our density. But what matters is that if this is the velocity of the particle, the kinetic energy, it will not fall into this potential. It will not fall into this potential, but it will fall in this one. Okay? So it is important that whatever is making the dark matter, well, in a way, let's put it the other way around. All this structure would collapse and form. The ones that do not collapse and form is because they are not there. And it's because the stuff escaped its own gravity. Okay? That's the right way to see it. Okay? I just put them in little pockets, and then some pockets evaporate and some other pockets do not evaporate. So if I'm telling you that as time evolves, these things become deeper and deeper because more stuff collapses into it, which basically means that the overdensity becomes bigger and bigger. But these ones do not. These ones will collapse and form a halo, and these ones will not. And where is the cut depends on the velocity of the dark matter. Because the dark matter is 5 times more abundant than the baryons. And so that's the thing that drives the gravitational potential. Okay? So in a way, the minimal mass of a halo that forms the stars forming galaxies depends on how the dark matter velocity is distributed. Okay? When you seed these perturbations, when these perturbations are set, and that's more or less matter radiation equality. Okay? So right before the CMB. So what I'm bringing you in a very qualitative way, but then you can perform cosmological computations, but what I'm telling you is it is important to know what's the velocity around of dark matter at the cosmological epoch. Not today, at matter radiation equality, when these things are seeded. Okay? And that proceeds that when dark matter is created much earlier, because it must be there at CMB, it basically depends on how it is created or not. It actually matters what's its velocity with respect to its mass. So if you want, what's the temperature of the universe with respect of the mass of the particle at the moment in which it decouples from the bath, at the moment in which it becomes disconnected from the universe. Okay? And if it's very hot, if it's relativistic, it will wash out structures. If it's not very hot, it will not wash out structures. Obviously, this statement that everything in physics is not binary. Okay? There's a whole range. But the point is that the simple fact that I can observe galaxies down to a certain mass rules out neutrinos, and Farinaldo is going to be talking about it later on, because otherwise they would wash out the scale of the dwarf galaxies, basically. You would not seed these gravitational potential wells, and they would not collapse into galaxies. It's clear the physical mechanism that leads to that. So one thing that I learned from the simple existence of up to a certain minimal mass is that dark matter must be warm or cold. It cannot be relativistic. Otherwise, it would wash out structures up to a point that the ones I see would not be there. Okay? So one more thing that I learned, and then I'm going to show you movies, is that it must be cold or warm. And it is now that I'm ruling out the neutrinos. But until this, it was allowed because it did not conflict with any of the constraints that I had set. It's actually extremely nice that you asked me the question. You see, every time I learn something new, I have to chunk something out. I can make hypotheses based on what I know, and then usually every new thing, it chunks out a little bit. You're falsifying a structure. The point is, again, there is no way to grow structures in this way and modify, to resemble the power spectrum today or the CMB with modified gravity. We can talk a little bit more about this. But so, this is how CMB and baryons, the density contrast goes up. And as you can see, the baryons are coupled with the photons around the CMB epoch, so they oscillate, okay? And then they reach the dark matter because they fall into the structures. And okay, this is these are the smallest scales, so how you set, but I'm going to give you these slides. But one way to see it is that the power spectrum of the dark matter gets cut at smaller scales if the particle is increasingly hot. And so all that power that would be there is basically cut. I don't want to get into the details of this plot, but for those of you who understand the power spectrum, that's what you expect to see. And you can set the minimal mass. The way I get information on the smallest scales, actually, it's summarizable into minutes. I'm going to get that, and then movies, and we go, since you arrived late. The way I learn about the smallest structures is actually interesting, and the fact is that emission and absorption happen more or less in astrophysics at exactly the same frequency, which is the Lyman alpha. This is the most common line. So I am sitting here, and there is stuff falling onto a black hole at very high redshift. Okay, and what happens is that this stuff gets excited to be falling into the black hole, and it emits on the Lyman alpha. Okay, but since it is at high redshift, I'm seeing that Lyman alpha shifted back. Okay, so it's a different central frequency, and it's a bigger line. Okay, so what I'm saying is that the stuff is emitted at a bigger lambda. Okay, so it's emitted here at this redshift, I don't know, whatever it is, 4, 5, 6. What happens is in between the line of sight, on the other hand, there's a lot of neutral gas. Okay, and this neutral gas, so actually here, so here is the neutral gas of different sizes, and here is the black hole that is emitting, so emission and absorption. This neutral gas is absorbing exactly the same frequency in the rest reference frame. It's another frequency when the light gets there. So what I'm saying is the big emission line, and then all these thin lines in between that are the absorption lines of the small objects between me and the line. And so actually all the small structures containing gas will give a contribution to that. Okay, and you can show that the actual details of that forest is called the Lyman alpha forest, give you information about the smallest structures. So yeah, of course you see dwarf galaxies, but below that you don't see them. There's just pockets of gas. And as a matter of fact, you can simulate the effect of, well, hot is already ruled out, but warm dark matter, and by comparing statistically the actual observation of the Lyman alpha forest that you expect from cold and warm, rule out certain warm dark matter scenarios because they would not form structures below a certain threshold. Okay, so that's basically the latest point. But again, so warm up to a certain level, but not entirely. So right now we are left with information from a host of things. We know from local observables that there is a dark component of matter. I call it dark because it's not luminous. I call it matter because it's not shining. It cannot be compact objects. I promise to dwell on it again, but I don't have the time, so ask me later on. I'll give you some details. I skipped a lot of details that I wanted to give you, but I hope I brought you with me to the fundamental points. I know it cannot be self-collisional and not collisional with the gas. So there is a limit that makes it, well, a threshold below which it can interact with itself and the gas, but it's kind of constrained. So it can be weak, or it can be at the order of this scale, but not at microscopic scales. And eventually I learned from cosmology that it really cannot be baryonic. Okay? And at this point, if I just, and also I learn that it cannot be relativistic at the time of matter radiation equality. Otherwise, I would not see the structures. It would wash them away. Okay? At this point, I ask myself, is it consistent with what I see? Well, I see these gravitational potential wells with the same power spectrum that I see from the CMB. I solve the equation of cosmology together with the equations of gravity, and I make them evolve. Of course, I need a computer for that. Simulations are not a bad thing because they solve equations. So here you're seeing the density contrast. Okay, it's dark matter only. I'm not including the gas. And you can see, and notice that it's not standing. You see, those things, the small things, are collapsing. They're moving. So these are the small original overdensities that are collapsing and collapsing, and the small ones form first, I was saying. They collapse first, and then they tend to collapse one on the top of the other. So they merge. Okay? And now you are at a redshift about 10, 9, This does not include gas at all. The coloring is just the density of dark matter. And only to reach these simulations has taken many, many years, because you actually have to solve the gravity equations on scales that are very different. Okay? But the thing is that if you solve the equations this way, this is a way to solve the equation, and you do it in a big enough box, even with dark matter only, which obviously must fail on small scales, obviously must fail, you get properties of the number of galaxies in the local universe, of the number of clusters, that resemble what we observe. Okay, so that phase order is extremely consistent. And another thing about modified gravity, people say, well, I can fix the galaxy in modified gravity, so you don't need dark matter. Try and form a galaxy with modified gravity, let alone the CMB. And obviously I'm not aggressing the modified gravity. I'm just saying, if I wanna find a solution, the solution must fit consistently everything I know. I cannot choose what observable to fix and not the others. And by the way, I did not devise the abundance of dark matter to fix the scales. I just took whatever I needed to fix the galaxies, or the cluster, or the CMB, put itself consistently in a cosmological context, and the structures come out. This is not constructed to produce that. Okay? This doesn't necessarily mean that's the correct answer, but it's the best answer we have so far. And still, we don't know what it is. We don't have a clue. Actually, I'm originally Italian, so I've been playing defense, which is what we do. I told you what it's not, but I didn't play attack. I didn't propose anything interesting. Okay? Now, while you think of questions, I throw you with simulations where there is actually gas, which is astonishing because you have to simulate the effects of the gas. It's the same thing cut in 4 parts, and you're seeing the temperature propagation, the star formation rate on the stars on the bottom right. I think the density is bottom left, and top right is probably the luminosity. So you not only form the gas and the stars, you track the light that is emitted by the stars and the contrast. And so the luminosity field, the radiation field, whereas there you see just the light of the single star, you're seeing the particles of stars. Okay, questions?
We take we take one question, and of course we have all the discussion session in the afternoon.
Write your questions down right now. Who wants to ask the question?
Just one question on the collapse model, the halo that you described. Do we have an estimate of the percentage of matter, be it dark matter or baryonic matter, that did not collapse at all into halos, into cluster of galaxies, and it's just in the cluster of gases?
Yes, it exists, and I don't know the number on the top of my head. So I can look it up for you, but...
Okay, so just before we leave for the coffee break, we have the presence list that I will circulate now for people to sign for this morning. And, okay, today apparently there was an issue. Several people could not get in time. That's a pity. But I hope tomorrow you'll be able to make it. So we started on time. And we will start on time after coffee break, so it will be a shorter coffee break. And just in case, tomorrow we'll be passing the presence list in the first 5 minutes of the talk to give an extra motivation for you to get in time, okay? So now, before you go to the break, be sure that you sign this sheet. Thanks.